So this lesson we're going to look at is to see what happens as we go to infinity with the limits. So today, rather than going to a constant, we're going to do something like this and look at the limit as x becomes infinite itself. So to help you get an idea of what's happening, let's take a look at a picture for this first graph. So that's the one I'm going to put into the graphing calculator. I'm going to use this one instead of the regular TI-83. This one has a little bit nicer, but you can plug it in into your calculator as well if you want to see. Or you can, of course, just follow along with me up on the board. So I'll pick a better range here. Okay. So there's something sort of interesting happening in this graph. So can anybody tell me what's interesting about this graph? I know nothing, right? It's math. But if we were to think of it like a mathematician, what's yeah, there is a reflection. That's a good good observation. There certainly is a reflection in that graph. There's some symmetry. But what else do you notice about it other than the symmetries? There's an asymptote there. Whereabouts? Yeah. So let's plug in. See that line? There'd be an asymptote right there horizontally. So far we've talked about vertical asymptotes, but we haven't talked about how do you find horizontal asymptotes. And that's really what we're going to be doing as we look for limits going towards infinity. So if I look here on this picture, as I go towards positive infinity, I end up with positive 3. And as I go towards negative infinity, I'm getting the same answer as positive 3. So from the graph, I can see that this is equal to 3, and this is equal to negative 3. So, of course, it's nice in calculus that there's a lot of visualizations of what we're doing, but we want to be able to figure out how to get that without needing a graphing calculator or a table of values to look at. So if we want to define a horizontal asymptote using limits, it looks like this. Basically, all we're saying is if you become infinite in the limit and the limit still exists, that means there's an asymptote on the graph. The only way it can occur is if the bigger and bigger the value of x gets, you keep getting tighter and tighter to the same value. That means you've got an asymptote in your picture. So there are some very, very common occurrences, and for those common occurrences, we want to be able to refer to them quickly. So there are some shortcuts here. Now, I will give you some shortcuts because it makes life easier when you're trying to go quickly through an exercise or something. But today you definitely want to think conceptually. I'll give you some conceptual tools as well, because if you know the conceptual tools, all the shortcuts won't matter. You'll have them in your head there. So here's a few shortcuts to get you started. What do you think would happen if I have a constant and I divide it by something like x to the infinity, right? What happens, or sorry, this number x becomes infinite. Maybe it's like 3 divided by x squared. And x is becoming infinitely large. What do you think happens? Yeah, it goes to 0. So any constant divided by something going to an infinitely large value, it's going to end up becoming 0 itself. It just cannot compete with the denominator there. And then one thing you should think of as well, sometimes it's hidden. For example, like this, that's the same thing as c 1 over c to the x, right? If I was to use my exponent laws. So we're really talking about the same situation. I have a constant on top and something that is growing infinitely large on the bottom. So in that situation, it's hidden, but it's going to do the same thing. So if you have some constant to negative infinity or something at exponential that way, it's also going to go to 0. And again, this is a continuation of the one we just talked about. This time x is going to negative infinity. So that means that's going to become infinitely small. It's also going to be a 0. So we should be able then just to quickly use those ideas and see if we can come up with a limit very quickly here. So what's the limit as x goes to infinity of 5 minus 2 over x squared? Genius. How did you get 5 so fast? 5 minus 0. Okay, so this one here, that's one of the situations we just talked about. So this one becomes a 0. So that means I'm just dealing with the limit as x goes to infinity of 5, which is 5. Okay, so this is where I mean it's handy to sometimes have some shortcuts because these kind of questions we can answer quite quickly. What about the next one? What will happen here? 3 over e to the x. Yeah, it's going to become 0. As you keep dividing 3 into more and more pieces, it's going to lose. There's going to be nothing left by the time it gets out to be infinitely large. All right. So we've talked a lot about 0 over 0 as an interesting limit. And today now we're going to talk about the other interesting limit, which is infinity over infinity. Right? So here's a picture of this graph, right, which is 5x squared plus 8x minus 3 divided by 3x squared plus 2. And what the graph's trying to show you is there is an asymptote that's happening here, and it's going to hug this line. It also does it on the other side too. If it kept going, you'd be able to see that asymptote as well. But again, we want to be able to predict this ahead of time. So let me give you an idea of how this works. One way that you could do it is we could divide out by the highest power. So here's one way that we could rewrite this limit. And the biggest exponent here is x squared. So I'm going to divide everybody in this fraction by x squared. So it's going to look like this now. 5x squared over x squared plus 8x over x squared minus 3 over x squared divided by 3x squared over x squared plus 2 over x squared. Okay, now why would I want to do that? Well, the reason why I want to do that is now I can talk about each piece in this limit. So what happens to, well, why don't I simplify it first, and then we'll talk about each piece. Okay, so if it looks something like that, well, 5 and 3 are nice because they're just constants. What happens to 8 over x? Yeah, so it's going to be a 0 as x disappears. 3 over x squared is also going to disappear. And 2 divided by x squared is also going to disappear. So that just leaves me with 5 over 3. So that's one way I could try to algebraically change that limit and come up with an answer here, which is 5/3, which is what we tried to say we wanted to predict. Okay. Does anybody notice something that might also be useful here? What do you notice about 5 over 3? It's really, I don't want to say it's obvious because it's not obvious, but it is kind of. Well, it's the asymptote, but where do you see 5 and 3? They're the coefficients of the biggest powers. Now, why do you think the biggest powers would be the ones we're concerned about? Right, well, we're going to get rid of the highest power. It's also the one that's the most significant, right? Out of everything in this limit, you know, if you're worried about something squared, that's much more significant than when you just do 8x. Like if I give you, you know, I wish I could give you $1 billion, that's awesome. If I gave you $1 billion squared, that is amazing, right? So basically what I'm trying to give you, the conceptual tool is when you're comparing x squared versus x, when numbers get really big, the x is not significant anymore. Squaring it is just gets so much bigger, so much quicker, that we can almost ignore that x term, right? It's the x squared that's going to matter the most. So really what we're considering here is we're looking at the limit as x goes to infinity of 5x squared over 3x squared. And if we just were to ignore everybody else, we'd have 5 over 3, and x is no longer a factor here. That's why I end up with 5/3, even though I'm going off to infinity. So here's my conceptual tool for you. I call this Bill Gates math, right? Because, for example, if you were Bill Gates and you had, actually, I think there's someone richer than Bill Gates now. I believe he owns a Mexican telecom company or something. But anyways, we'll still go with Bill Gates since he's more well-known. If I gave you, say, $5 billion, and then I said, oh, sorry, you know what? There's a bank fee. I have to take $3 out of there to put it in your bank account, right? How upset are you going to be? Very. Okay, yeah, you're all a bunch of cheapskates, I know, right? But in reality, you're just ecstatic that I gave you billions of dollars, right? So what you want to think about is, you know, if you had billions of dollars, what do you really care, right? $3 is kind of, you know, Bill Gates, probably the time it takes him to decide if he should spend $3, he's probably made like $100,000 in interest payments in that time. So it's really not worth him thinking about $3 because he might as well just do it and save himself the wasted time, right? So that's really, I'll show you some examples like with this, but again, think about what's the most significant part here, what's not significant anymore. So let's try some Bill Gates style of math here. Okay. So if I had, say, $2 billion and I took away 1, or 2 trillion and I took away 1, or 2 gazillion, I don't even know if that's quadrillion, I guess would be next. Right? How significant does that $1 become? Yeah, in your honest opinion, I know you're all a bunch of cheapskates. I get it. But as we go bigger and bigger, right? If you have $1,000 and I take 1 away, yeah, you're probably going to complain. If I have 10,000, I take 1 away. 1,000,000 and I take 1 away. Right, 1 billion, I take 1 away. 1 trillion, that $1 suddenly becomes less and less important, right? So that's what I'm saying here is, as it becomes less and less important, really this is what we're considering, which is just going to be 2, right? So what about the next one here? What do we have? What do we have for this next one? Yeah, 2 over 3. Okay, what about, now we've thrown this e to the x in here, which is kind of a problem. What's happening to this? It becomes 0. So again, whatever amount that's adding, it becomes less and less significant. We don't care about it anymore. For very, very big numbers, all that matters here is the limit as x goes to infinity of x over x, which is just 1. So if we looked at this on the graphing calculator, it would be a 1. Now, here's the challenge. Can you apply this conceptual idea if I change it on you, and now you have a 2x that's competing against a 3x squared? What's going to happen now? Why is it going to be 0? You're right. Yeah, the denominator starts killing it. Once these numbers get very, very big, you can't compete with just a linear compared to a quadratic. The linear is going to lose out. The bottom one here is going to win, and you end up with just 0. So how can you predict this if you're not sure about the conceptual way of doing it? Divide out the highest power is where we started. Oops, sorry. Sorry, my fault. Then on the bottom, I'd have 3x squared over x squared plus 1 over x squared. So this piece here would be a 0, gone, and that one simplifies out to 3. So I'd have 0 over 3, which is 0. Right? So you still can fall back to dividing out the highest power, but it's nice if you can do it conceptually, then that way you have a little less work to do. So what about this next example? What happens here? Yeah, it's going to be 0 as well. The bottom is going to win out. Even though this top, it's got all these extra pieces. You know, like if someone offers you, oh, $2 million cubed, and then I'm going to take 5 times 2 million squared. You know, it sounds good because you keep adding pieces, but really you just want the million to the 4th. It's going to be better eventually as numbers get bigger and bigger, it wins. Okay, So let's flip it one more time. What happens now that we're talking about this situation where I've still got two different powers and the top appears to be winning? Yeah, in this case, it's going to become infinitely large, okay? Because if you're trying to think who's winning out, you're going to have an infinity on the bottom divided by infinity, except this bottom piece is not nearly going to keep up to what the top is doing. So in this instance, it is also going to become 0. And again, if you're like, I'm not sure exactly where you're going, divide out the highest power. Let's see what happens. So 3x squared divided by x cubed plus 1 over x cubed. So 2 plus 5, sorry, that should have been an infinity, right? 2 plus 5 over x squared cubed divided by 3 over x plus 1 over x cubed. So these pieces on the bottom, that'll be a 0, that'll be a 0, that'll be a 0. So I just end up with 2 over 0. And we talked about this last day, right? What happens when you have a constant divided by 0? It's infinite, right? You're going to have an infinite limit here. So same thing happens when we deal with this situation here. The top is going to win. 2x squared will be the winner. So this is an infinite limit as well. So here's the shortcut that we just talked about. Again, I recommend you think conceptually, like who is going to win this competition? If there's a tie, it's the leading coefficients that are going to tell you what that final answer is. If the top is bigger, the top wins, it's infinite. If the bottom is bigger, the bottom wins and it becomes a 0. That's all these three rules here have to say. It tells you how to deal with it when the polynomials have the same highest exponent or bigger or smaller highest exponents. All right, so let's just see, what will we do with something like the limit as 3x minus 2 divided by square root 4x squared plus 1. It's kind of a challenge to think about this, right? Because, you know, who wins? Is it the bottom or the top? Which one's the better candidate here? Top, bottom? What do you think? All right, let's go ask Mr. Bill Gates how he deals with $3 billion and takes away 2. Well, again, let's think this way with really big numbers. If I have 3 times a trillion and I take 2 away, I know you're all horrified, but it's really not a big deal, okay? So as x becomes large enough, I don't care anymore about that minus 2. What else could you tell me is not significant when x becomes large enough? The plus 1 here is no longer a significance to me. I can really but think about this as the square root of 4x squared. So that means I've got the limit as x goes to infinity of 3x over 2x, which is 3 over 2. So there is no winner. They tie, and we end up with an asymptote at 3/2. All right, so do some Bill Gates math on the next one and tell me where you'll end up. Okay, so what do you end up with here? 1. Genius. So you're going to be dealing with this situation, which is just 1. Okay. Now let's think about, well, sine x over x. This is a strange one, right? Because if you're thinking about this, it's actually pretty easy to think about conceptually. We can prove it with a handy little theorem that you've learned about. But let's see what we have here. Can anybody describe why do you think it is that sine x over x goes to 0? Yeah, so sine x is between -1 and 1, but x can get as big as we want. So when you think who's going to win, well, for big enough values, the worst you can do here is get as high as 1, whereas I could be like a trillion on the bottom. So overall, that means the bottom's going to win this contest. The bottom is going to destroy the top, and it's going to be a 0. So if we wanted to prove it, I could say again that the sine of x is between 1 and -1. So -1 over x Whoops. We can do a quick sketch of the squeeze theorem. And if I look at the two pieces, I can use them to tell you what's going to happen to the sine of x over x. Right? Sine is stuck between -1 and 1. So I'm going to use the squeeze theorem to show you that as I go to infinity for sine x over x, these two bounds go to 0. Therefore, the middle one must also be a 0. Okay, so don't forget all those tricks that you've learned over the many years that you've been tortured through math, they still apply. So here's one way I could rewrite this. Split your fraction up. Now I'm dealing with the limit as x goes to infinity of 5 plus sine x over x. This is the limit as x goes to infinity of 5 plus 0, what we just talked about. So it's 5. Okay, so you have some strategies now. What I'd like you to try doing is, you may not have noticed, but I've done this intentionally. So far, we were always going to positive infinity. Now I'd like you to think about what's going to happen if we go to negative infinity, and we'll talk about some techniques on working there. So see if you can apply your techniques to these limits. You can try your graphing calculator to see if it, if your intuitions are correct. You can look at where the asymptotes are going to be, and then we'll talk about some techniques for dealing with negative infinity. So, have we had any luck here? Did people figure out a tactic, technique? Yes, what was it? Same thing we were doing earlier. Okay. Sure, if it works, right? But did you actually check in your graphing calculators too to make sure that things were the way they were supposed to? Yeah. Okay. Well, let's walk through it. Maybe it worked for you, maybe it didn't. You might get in trouble in negative infinities. You might get away with it. For example, if I had something like negative, let's do this the smart way. There. A big number like that. And I squared it. I'm going to get a very big positive, right? However, if I was to cube it, I'm going to get a very big negative. And that's where you can run into troubles because you may not have the right sign in your graph if you just went through the way we did before. So here's one way we can deal with it, and that's rewriting the limit. So we can make an equivalent limit, and as long as we play by the right rules, we can change this. So what if I wanted to say, well, we've been working with positive infinity. That's what I'd like to do in this question. How do you think I could make it so that it goes to the exact same place as it used to when it was negative infinity? Put a negative in front of it. That's exactly what we're going to do. So I'm going to go like this. Negative x cubed minus 1. Again, if you double check to see that this is in fact the same limit, as x goes to positive infinity of this expression, it's going to be equivalent to making it go to negative infinity in the other one, right? Because all of these pieces here go to negative infinity when I do that, right? So now that I've rewritten it, it's more convenient for me to work with. I have the limit as x goes to infinity, and this will be 5x squared because you square that x, negative x times negative x, it disappears. However, this time, that 3x cubed is negative, so there's going to be a positive x cubed. And on the bottom it's going to be minus, and this will be 4x cubed minus 1. So you might have gotten away with it, but this is in fact the equivalent form. The ones who win out, there's a tie. So the tie is going to be 1 over negative 4. when we actually find this limit. So again, you might have got away with it if you just used the original, thinking of things. However, you want to be more careful, and when you use negative infinity, you probably want to also look at making that replacement I've suggested. So why don't we try this next one here. You make your replacements with negative infinity, and then we'll see what comes out of this limit. Okay, so if I'm to do this as cautiously as possible, it'll be limit as x goes to infinity of 5 times negative x plus 3. And on the bottom here, I'm going to have the square root. It's still going to be x squared, but this is going to be minus 2x. So I'm going to have the limit as x goes to infinity of negative 5x plus 3. And on the bottom, I have the square root. This is insignificant as I get big enough, so that's what I'm going to drop out of this problem. I'd have 9x squared. This is insignificant, so the limit that I want to work with is as x goes to infinity of negative 5x over 3x. So this will become negative 5 over 3. That one you probably would not have gotten away with it if you did what we had done, just looking at 5 and 3. You might have gotten the wrong, maybe you got the right limit, but you might have gotten the wrong one if you did what we were just talking about a minute ago. Okay. We also need to talk about inverse trig functions here. We're not going to have time just right now, so I think what I'll do is I'll give you a bit of time to let these first set of things sink in, and then next block we'll talk about the inverse ones. So you can get a start on some practice. We will come back there, but let's just pause here. Okay, so we're going to talk about these inverse graphs. You guys know a bit about inverse functions already. We're just going to talk specifically about what's known as the arc functions, like arc sine, arc cosine, arc tangent, etc. So I'm just going to help give you an idea of where they come from, because knowing where they come from will help you reconstruct it if you do need to figure out something about them. And I'll show you how we use that in a second here. So for example, this is one cycle of the sine graph. To find the inverse, I don't need to keep repeating the same cycle because every possible value of sine is already shown. Now, do you remember what the problem is? If that's the function, will this inverse graph have a function? Do you remember how we figured that out? Some people are shaking heads. How do you know? If you look at this picture, you should be able to tell me, will it have an inverse that's a function?
No.
No? How come? Yes, this is a horizontal line. Yes, okay. So it's a horizontal line test, right? If I was to put a horizontal line through the graph, it fails here. If it fails the horizontal line, sorry, one second. If it fails the horizontal line test, that means you don't have an inverse, which is a function. That's a problem when we're trying to define nice functions. So we have to be selective about how we use the sine graph. So what I'm going to do is restrict the domain. And I think we talked about this when we were doing it in pre-calculus. So if you looked just at this picture here, can you see what would make sense to make, restrict it so that I do pass the horizontal line test? What x values will make it so that it passes the horizontal line test? Yeah, so genius. You guys have figured out exactly how the arc sine was created. That range right there from negative pi over 2 to pi over 2. If I restrict it there, that one little piece will then pass a horizontal line test. So that's where the arc sine comes from. You only look at this, well, I guess that's the arc. That one little piece that I've selected, that's what you apply the inverse to. So it's not the whole sine graph, it's only that one piece. So when you're talking about arc sine, it goes exactly back to this red piece that I've traced. So if the sine graph normally has a domain of all real numbers and a range, what's the range of sine again? Good, yeah, it's probably insulting that I keep asking you this, but negative 1 to 1. What do you know then about if I was to come up with a range, Having trouble phrasing my words here. If you know the range is from -1 to 1, what do you know about the domain in the arc sign? Sorry? Yeah, the x and y's switch, so that means this must happen. That's why you can't ask your calculator for like the arc sine of 5. It doesn't exist. It's not in the domain, right? Arc sine, by the way, is the same thing as the inverse sine. We're talking about the same things. Now, the range is a little bit trickier because the sine might have a domain of all real numbers, but what did we do to the domain in order to get arc sine? We restricted it. So what we did is we went from -π/2 to π/2, which means the range, the values that are going to come out of the arc sine, go from -π/2 to π/2. So if you understand how to construct it, see if you can do it for cosine by yourself. Because my opinion is this comes up so rarely when you actually, are being evaluated in calculus that it's the best strategy for you to apply is to know where it comes from. And I realize that's going to take you a few extra minutes to think about it in a test situation. But honestly, the trade-off between that and memorizing all this stuff is it makes sense to do that. So see if you can reconstruct the arc cosine using the picture of the cosine. Yes?
What is the range of -π/2?
Well, we restrict, see, we don't want to pick all real numbers or we don't end up with a function. So we restricted the domain. I think you actually just told me that I was going to restrict it here, right?
But you put it under the range.
Yes, because if the graph is from -π/2 to π/2, that means the inverse will have that for its range, right? X and y values are swapped, right? You switch the x and y coordinates for all the inverse points.
So the arc sine is the inverse of.
Yes, it is the inverse of the sine graph. However, it is a very specific part of the sine graph. It's just this part. That's it. Okay, so whenever you're hearing arc sine, you're talking about that one piece being the inverse, not the whole thing. That's why the domain and range don't go to all real. Okay, so cosine normally has a domain which is all real numbers. That causes a problem for us, though, if we're going to do the arc's cosine, because it'll fail here. The reason this is a problem is if I was to give my calculator, allow it to do arc cosine for any possible number, it would not be able to know which one you gave me, because here's two possible answers. It doesn't know which one it came from. So how does your calculator give you the answer? It could give you as many answers as you want. It still might not be the one you're talking about. But by restricting it, we know we're always talking about one specific set of answers. So what was your restriction on this domain? Yeah, 0 to pi. If we do this, you'll end up with a horizontal line test that you pass. Now, those of you who went from -π to 0, you are not incorrect. You're just a bunch of negatives, that's all. I don't know. The convention is to go from 0 to pi to pick the positive numbers. So this is the area you're going to use this arc here. So be positive about trig, okay? So the domain we're going to use here goes from 0 to pi. And what's the range for our cosine graph? Okay, so now tell me about the inverse. What do you know about the inverse graph? Okay, what's the domain for the arc cosine? Right. And if we flip it as well over here, that means I've got the restricted domain gives me my new range, 0 to pi. Okay, so let's take a look at how you might be expected to use these and some tricks for dealing with it. What's the arc sine of 1? Yeah, you don't know about arc sine, right? We haven't really practiced arc sine, so it can be confusing. But what you do know is this is the same question as saying the sine of something is equal to 1, right? Normally you go like sine of pi over 2 equals 1, right? You're used to going that way. If you're going in the inverse, it's backwards. You don't give me the angle and get a number. You get the number and you find the angle. So in this case, that's what I'm looking for, is what angle gives me an answer of 1, right? There's lots of them. You go, oh, there's pi over 2. There's 5 pi over 2. 7 pi over 2. And I have problems. I don't know the answer. But this problem doesn't exist in the arc sign, right? Those values aren't in it. That's the only one that's part of the arc sign. I know for sure this is the only answer because arc sign will only give me back one value. Okay? So you try them for arc cosine 0 and arc tangent is 0. See if you can figure out how would you do that dealing with the arc or the inverse cosine. So you're thinking about it the right way if you're trying to go cosine of theta will be equal to 0. You're trying to figure out what angle does that. So any ideas? Yeah, pi over 2 again. Okay, how about if I said arc tangent equals 0? Good, okay, so again, we're looking for where does tangent of theta equal 0? That means sine of theta over cosine of theta equals to 0. So I'm looking for where sine of theta equals 0. And that's going to happen at, 0. Right? There are many choices. However, with the arcs, you're only going to have what's restricted on that interval. So if we were to look and try to think, what do you think the restriction is on the arc tangent? Here's the tangent graph. What would make sense looking at that picture to have one nice curve that passes the horizontal line test? Yeah, so this is a nice curve right here that passes the horizontal line test. So I'm going to restrict it at negative pi over 2 and pi over 2. Okay. Let's just, for the sake of time here, let's just pick one. Would you like to deal with arc sine, arc cos, or arc tangent? Arc tangent? Okay. So what about this one here? How would we deal with that? Can someone give me an equation to get us started?
Use the special triangle.
Yeah, so we're going to need special triangles, and tangent of some angle is root 3. So the triangle, that's a terrible triangle. Let me see if I can. Okay, so I've got 1, root 3, 2, 60. Sorry, we're not in degrees anymore. Pi over 3 and pi over 6. So I want an opposite over adjacent to be root 3 over 1. So theta here has to be pi over 3. Now why is this in infinite limits? Well, let's put our thinking caps on and take a look at these two infinite limits which do rely on those inverses. Okay, so I have the limit as x goes to infinity. Can anybody, let's talk about the easy one here. What happens to this piece here? It becomes a 0, yeah. Now the other one's tricky. It'd be nice if I could go into my calculator and say, hey, arc cotangent. What's infinity, right? We have to think the other way, right? Instead of dealing with arc cotangent, I'm trying to say the cotangent of what value gives me positive infinity. So here's the picture of cotangent. Let me just, I'll change a few things on here so it's easier to see. So let's go negative pi to pi. Okay, so if we're looking at this one, how would you restrict the arc cotangent, knowing that we can't use this whole thing or we're going to fail the horizontal line test? 0 to pi, right, that makes sense again. So we're really, this is all I'm going to look at, 0 to pi. what value, okay, is going to give me an infinity if I'm using the cotangent? 0. Yeah, you can see it in the picture, right? Up here, maybe I should zoom out a bit more. Right? Up here, as I approach 0, I'm going up to infinity. So that means at x equals 0, I end up with an infinite amount. So that means the arc cotangent of infinity is going to be a 0. As you become infinitely large, the arc cotangent will give me back a 0. So 0 minus 0, not too exciting, it's just 0. Okay, so think about the next one. I'll leave the picture up in case you need to use it for discussion. This time I want to know about, as you head towards negative infinity, what will this limit be? Okay, so the first part of it doesn't change. This limit here is still going to become a 0. Okay. Now tell me about the next part, though. I'm trying to think what happens if I make the limit as arc cotangent. Oops, sorry. This is what I'd like to have, but I can't, you know. What's going to happen? Yeah, it's going to become pi. So really what I'm saying is what value of the cotangent is going to give me negative infinity, then negative infinity happens down here as I'm approaching pi. That's what you said to restrict it on, 0 to pi. So this must be the value at pi, so that too must have a value at pi. So that means my limit here will be negative pi. Now your graphing calculator can't do this, but I might as well show you since this one is capable. This one has this is why I recommend if you're going to download one graphing calculator, it's a free one. I can just switch x and y and then I can see its inverse. Oops, and of course I don't want all of that. We said we were restricting the domain, so let's go negative pi to pi. So my range will be from 0 to pi. And I have all real numbers here. That's the arc cotangent's graph, okay? And that's what the values are saying. As I go towards positive infinity, you see it's sloping down towards 0, right? As I go to negative infinity, 3.14, etc., it's getting up, it's making an asymptote at pi. Okay, so you need to be able to reason with the cotangent graph to get you into the arc cotangent. You won't have this luxury, right? But if you're comfortable with that, that's as far as you need to go with the arc graphs. So just to be clear again about what the expectations are, you should be able to know how to make that restriction, or you wouldn't be able to answer this graph. If you pick the wrong restrictions, you won't be able to know that the answer here is coming up at pi, right? Because you wouldn't know it was from 0 to pi. You also need to be able to work between, like we did here, arc sine of 1, making an equation using sine. And then, of course, if you can do that, you should be able to reason with the limits like we just did here. Okay? So I will give you the rest of the block then. Well, sorry, not the rest of this block, but maybe a good chunk of time here to practice these questions. While it's fresh in your head, I highly recommend you go right now and try some of the graphs that have arc cos and arc tan, all that kind of stuff in those practice problems.